Hey there, physicist. It's Mr. Clegg. Now we're going to do the Halliday book, chapter 2, number 18. All right, so Halliday, chapter 2, number 18. Chapter 2. Uh-oh. And we're going to do number 18. Okay, good. So I should have written that down before. Okay, anyway, now I got it written down. If the position of a particle is given by, and this is x is a function of time, I'll just write that, even though it doesn't say that in the book. Position is a function of time is given by 20t, right? Minus 5t cubed, right? Minus 5t cubed. All right, so where x is in meters and t is in seconds, so we got good units in there. When, if ever, is the particle's velocity zero? So we want to, first of all, we want to get the function for velocity, right? So we need to take, we know that the velocity v of t is going to be equal to the derivative of this. So we're going to take dx dt. All right, so that's going to be 20, right? Using the power rule. Minus 5t cubed, so we're going to go 3 times that. It's going to be minus 15. Oops, 15. T, drop it by 1, t squared. There we go. So there is our velocity function, v of t. We want to find out if that's ever equal to 0. We're definitely going to look at the graph of this in just a second, but I want to see if we can do this by using the algebra. So can we set that equal to 0 and see if we get a solution, right? So can we set, right? This is, let's see, is this, oh, this is A already, right? So part A of the problem, not A for acceleration. Part A of the problem is set V equal to 0. So we can set that equal to 20 minus 15t squared. Let's see what that does. So we get 20 equals 15t squared. And it looks like we can divide both sides by, so we could get t squared equals 20 over 15. So t is the square root of, and it could be the positive or negative square root of, it looks like there could be a negative time, right? Negative time just happens before we started the experiment. So there may or may not be any physical significance to that. Right? So yeah, so it looks like there's a 0 to that. And we're going to get, let's see what that number is. So it'd be 20 over 15. What is that? 3/4? 20 over 15, 1.33. So it's square root of, I think I'm not going to use radical notation. I'm just going to go ahead and square root that. Square root answer. And we'll get a decimal approximation. So, and it should be, whoops, let's see, 1.1547. So that could be, so right around there, uh, would be at that second. So plus or minus, we would be able to get that there is a time where that is. I'm going to pause this really quick while I set this up on Desmos, and then I'll show you. Whoops, pause the recording. Let's see. There we go. Okay, so I set this up on Desmos, and we want to see if there's a place where the velocity is 0. It should be plus or minus 1.15 seconds or so. All right, so we're going to just go ahead and go back to here, go back to Desmos here. So first of all, we want to see, is there a place where the velocity is 0? This is my position time graph that I'm showing. It looks like we have velocity 0 right here, where there's a flat spot. And that's just over 1.15, I think, something like that. Let's see. Oh, there you go. Look at that. And also we have one at the negative of that, negative 1.1. So that would be like before the experiment started, if there's a significance to that. We can graph the actual V function though, and we can see that, yes, indeed, right at that time thing, the velocity is 0, velocity shown in blue here. And back here, the velocity shown there as well. So nice to look at Desmos or look at a graph of some kind to to double check your work when you're doing this kind of stuff because it's very visual, I think. So here we go, back to this. Let's see if we can answer the next question. When is its acceleration a 0? Again, we could definitely do this graphically, but I want to do a little bit with I really like doing the graphs because I feel like I understand it better, but I also feel like it's good to practice the some of the ways that I'm not as strong in, which is just imagining this whole thing based on my algebraic thing. So if I want to get the acceleration, all I have to do is differentiate or take the derivative of the velocity. So it's going to be dv dt. So I'm going to take a derivative of this. Derivative of 20 is 0. So, and then I'm going to differentiate 2 times negative 15. It's going to be negative 30 and then t. So that looks like a line with negative slope and no intercept, right? So I'm going to get a line with negative slope of 30 and 0 intercept that'll go right through the origin. Okay, so that's what that looks like. Is there a time when the acceleration is 0? And it looks like the acceleration is 0. If you wanted to look at graphically, it would be right at the origin, the acceleration would be 0. So right at time 0, the thing would be 0. So if we wanted to set this equal to 0 and do it algebraically, set a equals 0, that's equal to negative 30t. So then t would equal 0, and that gives us a solution. Let's double check Desmos and check it out. Here's Desmos. And let's go ahead and I'll hide the velocity for a second. Now I'll show the acceleration. There we have our negative line there. Goes right through 0. There is definitely a time, and it is at time equals 0. Time 0, we have 0 seconds. So A equals 0 meters per second squared at time of 0. Okay, great. Oh, the other thing that I wanted to point out, this is kind of interesting. Back to this. Wherever the curvature, if you want to think about second derivative as, this is the second derivative. Wherever the curvature is 0, we have, so here we have a left-hand curve or an upward curve. And wherever the curve switches is where the second derivative is 0, which happens to be right here at 0 in this case. It's not always the case, especially so for example, if I change this, let's see, 5. Nope. Oh, there we go. So if I change this so that it's not, oh, that one's still at 0. Anyway, let's see. I wonder why that's the case. Nope, that one's always going to be at 0. Well, anyway, I am drawing a blank as to how to shift this over so it's not at 0. But yeah, that is a inflection point right there. And that happens when the second derivative is 0. Cool. We're going to go on to the next part of this so I don't make this video too long. All right. Next part. Uh, for what time range is A negative? That's C. And for what time range is A positive? So C. This is actually nice to just use the graph, right? So for what time range is A negative? And hopefully that's obvious that, that A is negative for negative times and A is positive for negative times and A is negative for positive times because it's just, I know I have just the derivative calculated here, but instead of showing what it is, but the acceleration is negative 30t. So it's just for all positive values of t, A is negative, and for all negative values of t, A is positive. So C asks us for what time range is A negative. A is negative for all t greater than 0. And D says A is positive for all negative t, all t, that's negative. And I think it says to graph them, right? And so it's kind of silly that they make you do all this stuff before graphing it, because I think the graph actually helps you understand it. So there we have, I know there, it's a little bit, let me see if, there we go. So there we have the original function in black. Did I mess it up? 20t minus 5. Okay. There's the original one. And then we have the uh, velocity function. And then we have the acceleration function. And again, if we wanted to think about the actual experiment starts at 0, we could just sort of, oops, we could sort of imagine chopping off everything that's to the left of, let's see if I can do that, chopping off everything that's to the left of 0. Ah, okay. And just taking positive values of time. But again, mathematically, there's a significance to the negative values, even if physically that there was nothing happening at that time. Okay, good luck. Let me know if you need help. See you in the next one. Bye.